Okay, so picture this scenario. It is a hypothetical, of course, so don't worry. But imagine you and I have been arrested.
Oh boy. I am already nervous. What did we do?
Let's say we pulled a bank robbery, the big one. But here's the snag. The police, they actually messed up the investigation.
As they do in these hypotheticals.
Right, exactly. So they don't have enough hard evidence to pin the actual robbery on us. They can only get us on a minor charge, maybe possession of stolen property or trespassing.
So they separate us.
Exactly. Separate interrogation rooms, absolutely no communication.
Yeah.
And the detective comes in and sits down across from me, and he offers a deal.
Let me guess. Testify against my
You
partner.
got it. He says, look, if you testify against your partner, that is you, and your partner stays silent, you go free, 0 jail time. You walk out the door right now, but your partner gets 5 years.
5 years. Wow. And I assume I'm getting the exact same offer in the other room. Betray him and walk.
You absolutely are. So now here's the math. If we both stay silent, meaning we cooperate with each other, the police can only nail us on that minor charge. We both get a slap on the wrist, maybe 6 months.
Which is manageable, I mean, compared to 5 years.
Ideally, yes. 6 months is great. But if we both betray each other?
Then nobody walks. We both get a medium sentence, say 2 years each.
Right. So sitting in that cell, sweating under the fluorescent lights, I am running the numbers. I know the best thing for us as a team is to stay quiet. But I am thinking, if you stay quiet, I should betray you so I go free, because 0 is better than 6 months.
Yeah, that makes selfish sense.
And if you betray me, I definitely have to betray you, just to avoid taking the entire 5-year sentence myself.
The logic is brutal. I mean, no matter what I do, your smartest individual move is to stab me in the back.
And that logic right there is exactly why artificial intelligence has historically been absolutely terrible at working together.
It really has been. I mean, that scenario you just described is the classic prisoner's dilemma. And in the world of game theory, that outcome, where we both betray each other, that is called a suboptimal Nash equilibrium.
Suboptimal Nash equilibrium.
Yeah. It basically means we are both smart enough to ruin it for everyone.
Smart enough to ruin it. That feels like a perfectly accurate summary of a lot of AI problems right now.
Oh, true.
But that is exactly the topic for today's deep dive, because we were looking at a fascinating new paper from February 2026 that tackles this exact tragedy of the selfish algorithm.
Yes, the paper is titled Multi-Agent Cooperation Through In-Context Co-Player Inference. It is a bit of a mouthful, but the implications are huge.
Right, so it is a collaboration between researchers at Google DeepMind and the Santa Fe Institute.
Oh.
And the big headline here for you listening is that they managed to get selfish, maximizing AI agents to spontaneously cooperate. And they did it without programming them to be nice.
That is the absolute key here. There is no altruism chip. There are no hard-coded rules saying, hey, don't be mean.
And this is the part that totally blew my mind. They didn't use some super complex, futuristic social brain architecture to do it. They used the exact same tech that is powering the large language models we use every single day.
Sequence models.
Exactly.
Right.
But the secret wasn't just the model itself. It was the environment they raised it in. Because it turns out, if you want trust to emerge, you need 2 things. You need diversity, and you need a surprising amount of uncertainty.
Okay, let's unpack this. Because usually when we talk about AI, we assume smarter is better. You know, we have self-driving cars, we have AIs passing the bar exam. So why is getting 2 bots to just share a cookie such a hard engineering problem?
Well, it comes down to a fundamental issue in reinforcement learning called stationarity, or rather, the lack of it.
Stationarity. Okay, give me the non-math version of that.
Think of it this way. Most AI training assumes the world stands still while you learn. So if you are a robot learning to walk, gravity is constant. The floor is solid. If you take a step but the physics don't change, you can try, fail, and try again because the rules are stationary. Right. Gravity doesn't just decide to take a day off to mess with you.
Exactly. But in a multi-agent game, like our interrogation room scenario, the environment isn't just the walls and the floor. It includes you, the other player, and you are learning too.
Oh, see.
So if I figure out a strategy to beat you, you change your strategy to counter me.
It is like trying to learn how to play tennis. But every time I figure out your serve, you change the laws of physics.
That is a perfect analogy. It is a moving target. And historically, researchers tried to solve this with brute force. They built what are called meta-learning agents.
Meta-learning. That sounds intense.
It is very intense. These are AIs that try to mathematically simulate the opponent's brain. They literally try to calculate, okay, if I do X, how will his neural network update? It requires you to essentially differentiate through the other guy's learning process.
That sounds incredibly expensive,
Yeah.
computationally speaking.
Oh, it is heavy. It is slow. And it requires you to make these really rigid assumptions about how the other guy thinks. And the researchers behind this paper, they basically said, let's scrap that. Yeah, they hypothesized that we don't need a special social brain that reads minds. We just need a model that is really, really good at predicting patterns.
Which brings us to sequence models.
Yeah.
Now, when we talk about sequence models, we're usually talking about things like ChatGPT, right? Predicting the next word in a sentence.
Correct. A language model sees a sequence of words like the cat sat on the show, and it predicts Matt. Well, these researchers realized that a game like The Prisoner's Dilemma is essentially just a conversation. It is a sequence of interactions. I did this, you did that. I got this reward.
So they literally treated the game history like a sentence.
Yes. They use the transformer architecture to predict the next token. But instead of a word, it is a move in the game. And they set up an experiment using the iterated Prisoner's Dilemma.
Okay, iterated just means they play repeatedly right. It is not a one-and-done deal like our bank robbery.
Right. They play 100 rounds with the same partner. A horizon of t equals 100. And this is crucial because it allows for a reputation to build. You know you can hold a grudge, you can forgive, you can signal your intent.
Okay, so they have their AI agent. Let's call him Agent Smith. They drop Agent Smith into this game. But here's the twist, and I think this is where the paper gets really clever. They didn't just put Agent Smith in a room with a clone of himself.
No, and that is the trap most researchers fall into. It is called self-play. If you train an agent purely against itself, they almost always spiral into mutual betrayal immediately. They know each other too well, and they just find that defect equilibrium we talked about.
So who is in the pool? Who is Agent Smith actually playing against?
So they created a mixed pool. Half of the time, Agent Smith is playing against other learning AIs, other guys who are trying to figure things out just like him. But the other half of the time, he is playing against tabular agents.
Tabular agents? That sounds like something from a 1980s spreadsheet.
It is honestly not far off. Think of them as very simple bots with a fixed lookup table personality. They don't learn, they just act. So one might be always cooperate, basically a saint who just lets you rob him every time.
Right.
Another is always defect, a total jerk who never helps. And another is tit for tat, which just copies whatever you did on the last round.
So Agent Smith enters the arena. He sits down. Does he know who is sitting across from him? Like, does he see a name tag that says, hello, I am the saint, or hello, I am another Agent Smith?
No. And that is the single most important constraint in this entire study. The agents are entirely anonymous. They get no agent ID. All they see is the game starting.
Wow, so round one starts.
Yeah.
Agent Smith has absolutely no idea if he is dealing with a complex learning AI or just a simple bot.
Precisely. He just has to make a move, say cooperate, and see what happens. Then round 2, then round 3. He has to look at the history of those moves and rewards and ask himself, who am I playing against?
He has to read the room.
Yes. The researchers call it in-context co-player inference because the pool is diverse, because there are saints and jerks and copycats. Agent Smith cannot just memorize one single winning strategy. If he plays always defect, sure, he easily beats the saint. But he gets punished by the tit-for-tat bot for the next 99 rounds.
Right. If you punch the tit-for-tat bot, it just punches you back forever.
Exactly.
So Agent Smith is forced to be adaptable. He has to figure out the pattern of the other player on the fly and change his behavior to match it within the episode.
And they proved this happens. They showed that within a single 100-round game, the agent successfully figures out who the opponent is and switches to the optimal strategy for that specific opponent. That sequence model acts as a really fast learning algorithm.
Okay, so step one is diversity creates adaptability. If you raise a child in a village with all kinds of weird people, they learn to be socially flexible.
Exactly right.
But, and this is where I think the paper takes a bit of a dark turn, being adaptable isn't always a good thing.
No, it is not.
Because usually we think of adaptability as smart. It is evolutionary. But the researchers found that being adaptable can actually make you a victim.
Highly vulnerable, yes. This is step 2 of their mechanism. Imagine you are playing against someone who adapts very, very quickly. If I hit you, you back off. If I smile, you smile. You are essentially acting as a mirror. You are constantly optimizing for the best result, given whatever my behavior is.
Okay, so if I'm the mirror, what are you?
I am the manipulator. If I realize you are a mirror, I can learn to be stubborn. I can essentially say, I am going to defect betray you, 40% of the time. And I know you are going to keep cooperating the other 60% of the time because you are smart enough to know that if you fight back, I will burn the whole house down and we both get 0.
That is just blackmail.
In game theory, it is literally called extortion. There is actually a famous paper by Press and Dyson from 2012 about this. They discuss zero-determinant strategies. Basically, if I know you are a naive learner, someone who is just trying to adapt and maximize your score right now, I can force you into an unfair deal. I take the bigger slice of the pie and you let me do it because getting a small slice is still better for you than getting absolutely nothing.
Man, so let me get this straight. They trained these agents in the mixed pool, and the agents learned to be adaptable, but then the researchers froze one of these adaptable agents and they trained a new predator agent to play against it. And the predator turned into a bully.
It did. The predator learned to perfectly exploit that adaptability. It forced the learner into unfair cooperation, maximizing its own reward entirely at the expense of the learner.
This sounds like a recipe for a completely toxic society. I mean, we have an environment that is just creating victims and bullies. How does this possibly lead to the nice cooperative outcome we were promised at the start of the show?
This is the paradox. What happens when two bullies walk into a bar?
A fight.
Or a stalemate. Imagine Agent A is an extortionist. It is trying to bully Agent B, but Agent B is also an extortionist trying to bully Agent A.
So they're both stubborn. They're both trying to say my way or the highway.
Exactly. They are both learning aware. They both know the other guy is trying to manipulate them. And because neither one is willing to be the victim and neither can force the other to submit, the only stable outcome that generates any points at all is for both of them to back down and cooperate fully.
Wait, really? So they cooperate not because they want to, but because they tried to exploit each other and failed?
Yes. It is a robust equilibrium born entirely of mutual extortion. It is exactly like two nuclear powers realizing they can't win a war, so they just sign a peace treaty.
That is surprisingly cynical, but also incredibly hopeful somehow.
It is highly effective. The researchers found that this mutual cooperation was incredibly stable. But remember, you only get there because of the chain reaction. You needed the dumb bots, the tabular agents, to force the AIs to become adaptable in the first place. Once they were adaptable, they became capable of extortion. And once they were capable of extortion, they basically forced each other into peace.
It is an evolutionary ladder. You can't just jump straight to the top. You have to go through the messy middle.
Correct. And that messy middle is exactly where the sequence models shine.
Okay. I want to geek out for a second on the how. We mentioned sequence models, but the paper compares two specific algorithms, A2C and PPI. What is the difference and why does it matter for you listening?
So A2C is a standard reinforcement learning method. It stands for Advantage Actor Critic. It is what we call model-free. That means it looks at the board and asks, what is the best action right now? It doesn't really think about the future or simulate the world. It is highly reactive.
Like a reflex.
Right. PPI, on the other hand, predictive policy improvement, is the new method they introduced in this paper. It uses that sequence model as a true world model. It actually runs a simulation in its head.
Like a mental sandbox.
Exactly, a mental sandbox. Before it makes a move, it runs what are called Monte Carlo rollouts. It asks, if I cooperate, what will likely happen next, and then what? And then what? It predicts the future actions, observations, and rewards.
So it is actually planning.
It is planning inside the context of the conversation. And because it is using that transformer architecture, just like an LLM, it is incredibly good at picking up on those really subtle patterns in the opponent's behavior. The paper showed that while the standard A2C could eventually learn to cooperate, the PPI agent was much faster and way more effective at that reading the room part.
It effectively has a theory of mind. Or at least a statistical simulation of a mind.
A statistical simulation of a mind is actually a pretty good definition of empathy if you squint hard enough.
Now, skeptical listeners might hear this and say, maybe this was just a fluke. You know, maybe they just got lucky with the random seed generator. But the researchers did something called ablation studies to prove their point. And I love ablations. For those listening, it is like taking a car engine apart piece by piece to see exactly which part makes it run.
And the ablations here are really definitive. The first thing they tried to remove from the engine was the uncertainty. They gave the agents ID badges.
So they told them exactly who they were playing against right from the start. You were playing against tit for tat.
Or you were playing against learning agent number 45. They give them perfect explicit information.
Now, logically, you would think this would make them perform better. I mean, if I know who you are, I should be able to cooperate with you faster. I don't have to guess.
You think so, but cooperation completely collapsed
It collapsed.
because they didn't need to read the room anymore. Since they knew exactly who the opponent was from round one, they didn't need to develop that general purpose adaptability. They just memorized a static response for each ID. Oh, it is Agent 45, I defect. Oh, it is the saint I exploit.
They stopped thinking and just started looking up answers in the back of the book.
Exactly. And because they stopped being adaptable, that whole complex dynamic of mutual extortion never kicked in. They just became completely selfish again.
That is mind-blowing to me. Giving them more information actually made the society worse.
It heavily suggests that uncertainty is actually a prerequisite for this type of robust cooperation. You have to not know who you are dealing with in order to develop the social intelligence required to cooperate.
Okay, and what about the other ablation, the village?
Right. They removed the mixed pool, they took away all the dumb bots, the saints and the jerks, and just had the smart learning AIs play against each other from day one.
And let me guess, disaster.
Total disaster. Without the easy money from the dumb bots, the agents never learned to be adaptable. They just spiraled into defection immediately. They needed that diversity to bootstrap their intelligence.
So to get a smart cooperative AI, you actually need to raise it in a chaotic environment full of uncertainty and completely different kinds of people. You cannot raise it in a sterile lab.
That is the big takeaway here. The paper argues we don't need to invent new, complicated social brains or ethics modules for AI. We have the models. Foundation models, transformers, they work. We just need to rethink the curriculum.
It really bridges the gap between LLMs and these multi-agent systems.
It essentially says that in-context learning, which is what ChatGPT does when you talk to it and it adjusts to your tone, is the actual mechanism for social coordination. It acts as this fast learning algorithm that runs inside the interaction itself.
So what does this mean for the future? Are we going to see armies of bots negotiating for us?
We are definitely moving toward foundation agents. We have foundation models for text. The next step are agents that take action in the real world on our behalf. And this research suggests that if we want them to be cooperative, we shouldn't train them in perfect, transparent environments. We should train them in mixed, somewhat opaque pools where they have to figure things out on the fly.
It is funny, isn't it? We always talk about transparency as the ultimate good in society. You know, if we just had perfect data, the markets would be efficient. Everyone would trust each other.
But this proves the exact opposite.
Right. It proves that hiding information, removing those name tags, actually created a much better social outcome. It forces us to really ask, is mystery actually the glue of society?
It is a profound question. I mean, if I knew exactly what you were going to do in every single situation, if I had a perfect prediction of your behavior, would I ever bother to negotiate with you? Would I ever bother to build trust? Or would I just optimize my path around you like you were a piece of furniture?
It is the uncertainty paradox. We strive for certainty, but we seem to actually thrive in uncertainty.
Uncertainty forces us to treat the other person as an agent, not an object. And that, it turns out, is the actual seed of cooperation.
Man, what a powerful lesson from a couple of algorithms playing a prison game. I'm definitely going to be thinking about that mutual extortion handshake for a while.
It is cynical, but it works.
That is it for this deep dive into multi-agent cooperation through in-context co-player inference. Thanks for helping us break it all down.
Thanks for having me. This was fun.
And for you listening, check the show notes for a link to the paper if you want to brave the math yourself. Until next time, keep diving.